Hi everyone! After a series of videos about the Duender project and Klipper firmware, there is still one question left unanswered: how to set up the firmware configuration for your printer. In this video, using my Duender with the Bigtreetech Manta M5P control board as an example, I'll not only show how my configuration is set up, but also try to explain the logic I usually follow. I'm not going to cover every feature of Klipper or the Manta M5P because that could make this video many hours long. Today we'll focus only on the basics, essential parameters you need to set so your printer can start printing. I've already explained how to install the Klipper host and MCU in a separate video series. However, to make this video more or less standalone, I'll show you how I installed Klipper specifically on my Bigtreetech Manta M5P board. I download the full image for the host system and write it to an SD card using RPI Imager or Balena Etcher. In my case, it's a Bigtreetech CB2, so the speed and quality of the SD card isn't critical. In the end, the whole system will be copied to the internal eMMC memory and run from there. For this, the CB2 image includes the NAND SATA install tool. How to use it is explained well in the instructions, but I recommend running it after you've set up all the system. Once the image is written, you need to set up Wi-Fi. The principle is usually the same. You edit the parameters in the configuration file stored in the boot partition on the SD card. The file name and syntax may be different, so check your module's documentation. Insert the microSD card into the slot next to compute module on your board. Now connect the board to power. We'll go over what to connect and where during the process. All Bigtreetech boards, as well as most other universal boards, have detailed pinout available on GitHub or the manufacturer's website. Even many proprietary boards often have at least a partial pinouts that are enough to understand where everything goes. In my case, the pinout not only shows port names, but also the name of each pin. Pins labeled PA, PB, PC, and PD are the microcontroller pins. Some are routed directly, but more often they go through components like MOSFETs, inverters, or filters. These pins are used in Klipper to send commands and read data. The pinout also shows all communication ports, SPI, CAN, UART, and so on, as well as GPIO ports for the compute module, but we won't need those today. At this stage, all you need to do is connect power wires. Most modern boards support from 20 to 24 volt power. Some have two separate power inputs, one for the motors and another for everything else. This allows you to power the motor separately from the rest of the electronics, for example with 48 volts. On some boards you need to connect power to both inputs, even if they come from the same power supply. On the Manta board, motor power is controlled by jumpers. If you are using a single power input, the jumpers should be placed on the VM and VBB pins next to each motor. If you are using a second power supply, place the jumpers on the VM and HV pins for the motors that will use the second port. I am powering everything from the single 24 volt supply, so the wires go only to the DC in port according to the pinout. Then power on the board. Give the board a few seconds to boot. If Wi-Fi was set up correctly, it should get an IP address. You can find it with an IP scanner, for example. Then connect to the board over SSH. I use PATSI. For Bigtreetech boards, the login is BigU and the password is BigU. Update everything you can. At this stage, you can also install the Kiauch package. We won't need it right now, but it will be useful later. Kiauch also lets you update all Klipper modules. Next, run make menu config and follow the official instructions for configuring the firmware builder. Compile the firmware. There are two ways to flash it, using an SD card or DFU mode. Both are explained in the instructions. I prefer the SD card method. I download the firmware via FTP, rename the file to firmware bin, write it to an SD card, insert the card into the full-size SD slot on the board and power it on. If everything was done correctly, the file on the SD card will be renamed to firmware car. Now, if you go to the board's IP address in the browser, in the web interface, open the Machine tab, Devices, and you should see the board connected and recognized by the system. Now we can move on to configuring the printer. As I mentioned in the Klipper video series, There are ready-to-use configuration files for a huge number of printers. Often you just need to upload one into Klipper and almost everything will work right away. There are also partially prepared configs for universal boards, which still need to be adjusted for your specific printer. If you can't find a config for your board on GitHub or user forums, things get more complicated. You have two options: manually port the pin parameters from another firmware if its source code is available, or physically trace the board to map the pins yourself. Both methods are time-consuming and difficult, so we won't cover them in this video. If you run into a board like this, think carefully. Is it really worth spending your time trying to run an unknown board with the questionable capabilities? Even if you get it working, later on when you want to add something or modify your printer, you'll keep running into connection issues. In such cases, it's much more practical to spend some money on a modern universal board that already has a ready-made config. That will save you a lot of time. So let's assume we already have some kind of config. In my case, it's a board config that needs to be adjusted for a custom printer. There can be a lot of configuration files. Depending on the image you installed, some extra modules might already be included, for example Obico, a service for remote control over the internet. But right now we are interested in the main file that defines the printer's configuration, printer CFG. Copy the full config for your board from the Klipper GitHub page and paste it into printer CFG on your printer. You can also find example configs directly on the host, but I prefer downloading the versions from GitHub. Let's go through it step by step. Include mainsail, connect the configuration for the mainsail web interface. If part of the configuration is stored in other files, for example in mainsail CFG, you need to add an include line with the file name to printer CFG. Then all the settings from that file will also be applied. Include Moonraker Obico macros. As I said, this connects the remote control module, MCU CB2 and the serial address, basically assigning a name to the host. These lines aren't necessary, but it's better to keep them if you plan to use the host's GPIO pins in the future. Then there is the line include generic Bigtreetech x66 CFG. Sounds like adult movie, but no, it's just suggesting that you load the board config from a separate file. Since we already copied the board config into printer CFG, we don't need this line. Next comes one of the most important lines. In the example it's at the bottom, but we'll move it up. The MCU block. Here we need to set the address the host will use to communicate with the printer's mainboard. Find the address in the devices menu and replace the one in the config with it. The MCU section also had other options, like connecting over CAN instead of serial port. You can read about this and many other features in the configuration reference on the Klipper's official site. It has a lot of information about almost all major Klipper features and their settings. Some topics even have separate sections with more detailed explanations. If you plan to experiment with Klipper and add new features and devices, this page will be one of your main resources. Honestly, I don't know most of Klipper capabilities. There are just too many. So here I only go over the more standard and common solutions. And another quite useful function is MCU with My Extra MCU. I've explained before that Klipper can connect multiple control boards or other devices to a single host. For example, my custom multicolor system Medusa uses an extra board that connects to the main printer this way. For that, I have an MCU MMU block with its own serial address. Klipper can work with all the pins on the extra board synchronized with the main one. You define them in the format MCU name, in my case MMU, followed by colon and pin name on that board. The next required block in the config is printer. Here you need to set several main parameters. The most important one is the kinematic, and there are quite a few options. However, the vast majority of printers use either Cartesian or CoreXY kinematics. In a Cartesian printer, the axes are independent of each other, and moving along one axis only require one motor to move. This group includes all bed slinger printers and those with what I call MakerBot style kinematics, where one stationary motor moves the entire y-axis and the x-axis motor moves along with it. In the CoreXY, both motors are stationary and linked together. When only one motor moves, the printhead travels diagonally rather than along a single axis. To move along the axis, both motors must move in sync, either in the same directions or in the opposite directions. Delta printers are also quite common, where all three motors move together in a complex pattern. I've never configured a Delta printer from scratch, and they have a lot of specific details, so I can't cover them here, at least for now. There are also CoreXY printers, though I personally don't see much point in them. The rest are rare and hardly used by anyone. Next, you must specify a few more printer parameters: the maximum speed and acceleration for axis movements. These values can be temporarily changed during operation with the commands, but if a G-code file contains a movement command with a higher speed or acceleration, it will still be limited by the maximum values set in the configuration. You can also set separate maximum speed and acceleration for the z-axis. This isn't mentioned in the configuration reference, but it's present in almost any config. There are also extra motion parameters you can set. They are not necessary. If you don't include them, default values are used automatically. For the initial setup, we can skip them, and later, during calibration and tuning, you can experiment with these values. The next required blocks we need to configure are the axis motors. Let's start with a bit of basic theory to understand how stepper motors work. Simply put, a motor has two closed loops made up of electric coils arranged around the stator and permanent magnets on the rotor. The motor works by following a precise sequence of electrical pulses sent to these loops. These pulses are generated by a stepper driver, and the driver itself receives simple commands from the microcontroller, telling it the direction and number of steps through the step and dir pins. There are many different types of drivers, but we'll focus on the most common ones. The most widely used are drivers with the TMC chips from Trinamic. They can be soldered directly on the board or installed in the dedicated port on the board. Next to these ports, you'll usually find a bunch of pins without clear labels. This is because, depending on the driver, it can support multiple control or communication protocols. The oldest, now almost unused, is standalone mode. In this mode, the driver can only be manually set to a certain microstepping mode by placing jumpers on these pins according to a specific scheme in the manual. What are microsteps? In short, every motor has something called a full step, which is when the permanent magnets on the rotor align with the coils inside. On most motors, one full step turns the motor by 1.8 degrees. Less commonly, there are motors with a 0.9 degree step. But the driver can send power to the coils in the special way, stopping the motor at intermediate positions. This is called a microstep. The driver divides a full step into segments like 160, 132, 164, and so on, improving precision and making movement smoother. In standalone mode, besides setting microsteps, you also have to manually adjust a variable resistor to set the Vref, the voltage that defines the motor's maximum current. This is done using formulas for your specific driver and motor. But as I said, standalone drivers are almost never used in modern printers. If your board has such drivers, I recommend upgrading it to something new. Most modern Trinamic drivers work differently. They have extra pins for UART or SPI protocols, which allow you to control all driver settings through the configuration. With TMC2209 drivers, UART is used. On older boards, when this feature was new, connecting via UART or SPI meant soldering jumpers on the drivers, adding wires, plugging them into special ports on the board, and doing a lot of setup work. On modern boards, for UART or SPI connection, you just need a compatible driver, place one jumper on the board, configure it, and everything connects internally. The config already has settings for two driver types: TMC2209 using UART and TMC2130 using SPI. You need to uncomment the lines for the one you use or find the parameters for your drivers in the configuration reference. For TMC2209, the UART pin is already specified. Next is run current, the working motor current in milliamps. You can find this in your motor specifications, or, to be honest, I usually set it by trial and error. I start with a 0.8. If the motor skips steps, I increase it a bit. If the motors get hotter than 70 degrees Celsius, I reduce it. You can also set hold current to a lower value, so when the motor is holding position without movement, it doesn't heat up with the full current. Next, diag pin is used for sensorless homing, which I'll cover later. There is also an optional parameter, stealth chop threshold. A quick explanation. TMC drivers has two operating modes, stealth chop and spread cycle. Stealth chop is quieter, a bit smoother, but weaker. It's usually fine for accelerations up to about 7,000–8,000 mm per second square and speeds of 200–300 mm per second. Beyond that, you need to switch to spread cycle, which is slightly louder but can handle much higher accelerations. The stealth chop threshold parameter lets you set the speed at which the printer will automatically switch to the more powerful spread cycle mode. However, switching during the print often causes a jerk that can affect print quality, so people usually set it to either a very high value, so the switch never happens, or to 0, so spread cycle is always on. Given the speeds my Duender prints at, spread cycle is only mode that works for me. All drivers also have many advanced parameters, and different combinations affects how efficiently and precisely your motor runs. Ideally, these parameters should be fine-tuned for each motor individually. However, the default settings usually give acceptable results even without adjustment. Manually tuning all of this is basically black magic. There is a Klipper plugin called TMC Autotune. In short, it can automatically configure all these parameters and has many ready-made presets for different motors. I won't to go into it now, maybe another time. You need to set driver parameters for every motor that uses a UART-controlled driver. Now back to configuring the motors themselves. Every motor, including the extruder, has three main pins. The step pin, which triggers a step, the dir pin, which controls direction, and the enable pin, which allows the printer to turn the motor power on or off. On my board, the motor outputs are arranged as follows. The first two drivers and motor outputs are meant for the X and Y motors. In the CoreXY setup, they are usually called A and B because they don't correspond directly to the main axis, but in the configuration they are still labeled X and Y. I'll keep calling them that to avoid confusion. The third driver is for Z-axis, and it has outputs for two motors wired in parallel. That means that two Z motors move in sync from one driver. I had a similar setup on my old E3 mini board. The remaining two drivers and outputs are for two extruders, which is also clear from the extra ports for a second heater and thermistor. But that doesn't mean you have to use the motors exactly as manufacturer intended. For example, my Duender has one extruder but two Z-axis motors. With independent control of both Z motors, you can use a useful feature called Z-tilt alignment. That's why I connected the second Z motor to the first extruder port and plugged the extruder into the second extruder port. Then in the config file I reassigned the pins for Z and extruder according for this wiring. Note that some pins have an exclamation mark in front of them. This means the pin is inverted. For the dir pin, adding or removing the exclamation mark changes the axis movement direction. And if you didn't know, you can also reverse the motor's direction by rotating its 4-wire plug 180 degrees. And here's another useful tip. Not all motors have the same wiring scheme. For example, most Creality motors have the middle wires in the cable crossed, while almost all other motors use a straight cable. If you connect a motor and it just twitches oddly, like it's trying to move but can't, try swapping the two middle wires. Your motor might have a different pinout. Next in the motor settings is microsteps. This doesn't work with the standalone drivers, but for UART or SPI connected drivers, you can set the number of microsteps here. Which microstep settings is best? It's all about balance. Theoretically, the more microsteps, the smoother and more precise the motion. But it also means the host has to generate and the microcontroller has to process far more step signals for the driver. If you push the microsteps too high, your host or microcontroller might be overloaded, causing skipped steps or even a full shutdown. Usually 132 or 164 microstepping is enough. Beyond that, the difference is barely noticeable, but the system load increases dramatically. For the Z-axis, you can set a higher since it moves less and extra precision can be helpful. Modern drivers also have an interpolation feature in addition to microstepping. You can enable it in the driver block. With interpolation, the driver generates extra intermediate steps between the real microsteps, bringing the resolution up to 1 to 256. This can make motion smoother, but it doesn't affect accuracy at all. Next is a very important parameter, rotation distance, which is how far the axis moves for one full motor revolution. Most firmware uses a different parameter, steps per millimeter, which is how many steps it takes to move the axis 1 millimeter. If you have that value from another firmware for your printer, you can use an online converter to get the rotation distance. In most board config examples, the XY rotation distance is set for 20-tooth motor pulley with a GT2 belt, which equals 40 mm. For the Z-axis, it's often set to 8, which matches a 4-start 8 mm lead screw with a 2 mm pitch. This is a common setup and may work for you right away. You can fine-tune it later. If your motion system is different, you'll need to calculate it based on your hardware. There are several calculators online, and I leave a link to one in the description. The extruder is similar. The calculator has a separate function for it. To calibrate, you feed filament through the extruder and measure it. There is plenty of info on how to do this, but my tip is to run the filament without a nozzle or hot end installed, so extra resistance doesn't affect the results. The next essential parameter for the printer to work is endstop pin, which tells the printer where its 0 points are. My board has 4 endstop ports, one each for the X, Y, and Z axis, plus one for the extruder, which is configured separately as a filament runout sensor. Endstops come in two main types, mechanical and contactless. Mechanical ones are simple microswitches with a button. When pressed, they just open or close a circuit between two wires. The switch itself has 3 pins, C common, NO normally open, and NC normally closed. It only needs 2 wires to work. If you connect C and NO, the circuit is normally open and closes when pressed. With the C and NC, it's the opposite, normally closed and opens when pressed. There is no real difference in how it works. If the logic is inverted, you can either swap the wires or add an exclamation mark to the pin in the configuration, like we did for the DIR pin. On the board, the 2 wires connect to the signal and ground pins of the endstop port. Polarity doesn't matter. Sometimes these microswitches are mounted on a small PCB with a pull-up resistor and sometimes with an LED. Such sensors need power. They have 3 wires and should be connected to signal, ground, and VCC on the board. It's worth noting that most of my endstops came from old Creality printers. They are all soldered on a small PCB with labeled pins signal, ground, and voltage, even though there is no resistor or LED on them. In reality, those pins are just C, NO, and NC, and you only need to connect 2 wires. Contactless endstops are most often optical and less commonly inductive. These sensors always require power and have 3 wires. They connect according to their pinout, which is usually correct. Also, sometimes in the configuration, the endstop pin has a caret symbol, which enables the internal pull-up resistor. It needs to stabilize the signal, especially with the simple endstops. Simply put, if the example config shows a caret, it's better not to remove it. It won't hurt. On top of that, modern drivers has a stalwart feature that allows for sensorless homing. Sensorless homing works like this. When the axis hits something, the motor is blocked, causing the coil current to change. The driver, like TMC2209, detects this change. When it happens, the firmware assumes the axis has reached its end. The big advantage is that you don't need to think about where to mount end stops or run wires to them. The downside is that it's not the most precise method, though for X and Y axis that's usually fine. In short, to enable sensorless homing, you need to place small jumper on the diag pins next to the relevant drivers, connecting the driver to the end stop port. Then in the config, change the end stop pin, for example for X, to TMC2209 stepper X, virtual end stop. The pin that was assigned to the end stop should be set as diag pin in the corresponding driver's config block. You also need to set driver stalwart threshold or sensitivity. If it's too low, the axis won't stop even if it's crashed into the edge. If it's too high, the axis will stop halfway or even trigger without moving. You need to find a middle value so the axis doesn't hit too hard but still reaches the end reliably. For the sensorless homing to work well, it's a good idea to add custom parking macros and fine-tune the sensitivity so the system runs smoother and more reliably. We won't go deep into that now, this video is already getting long. For the Z-axis, sensorless homing isn't a great option because of lower accuracy, but often the end stops are replaced with the auto-leveling probes. Again, this is the big topic and would take a lot of time to explain, so here is the short version. Build touch type probes mechanically touch the bed with the pin. In my opinion, they are the simplest and most universal option. These probes use 5 wires. They need coil control to raise and lower the pin, and they also send data from the whole sensor. Most modern boards have a dedicated build touch port, so it's hard to connect it wrong. The pins are usually listed in the commented block in the config. For correct operation, you'll need to set the probe offset from the nozzle in millimeters. My XY offsets are negative because the probe is in front and to the left of the nozzle. Moving it back or right would make them positive. The Z offset can only be positive and equals the distance from the probe trigger point to the nozzle tip. There are plenty of guides on how to calibrate and set this up. The second popular option is inductive probes, which detect metal underneath them. They have only 3 wires. On the Manta there is a dedicated port for such probes, with a switchable power voltage, since this sensor can work on different voltages. There is also a modern high-speed, high-precision probe called Eddy, but I haven't worked with one yet. And as far as I know, for the Duender, many people also use homemade removable probes like the Clicky probe. It's a solid option, and if you want more detail, you're welcome to my Discord server. There is a lot of cool stuff going on there, and the people are great. For auto-leveling, you also need to configure the bed mesh block and add a safe homing macro, so the Z-axis parks in the center of the bed, preventing the sensor from trying to make probe in mid-air. The last important movement-related settings are the min-max travel limits, movement directions, and end-stop locations. End-stop position is the coordinate where the print head ends up when the sensor is triggered. It can be 0 if the nozzle is right at the edge of the bed in the home position. It can be the maximum value if the end stop is at the far end of the axis. It can also be more or less than these values if the print head can travel beyond the bed area. Position max obviously set the maximum coordinate of the print area, or the end stop coordinate if it's at the end of the axis. If the end stop position is less than 0, like on my setup, you'll also need to add position min with the same value as the end stop. But where are these points supposed to be, and which way should everything move? On the classic FDM 3D printer with the rectangular bed, the 0 point is always in the front left corner of the bed. Increasing X moves the head to the right, increasing Y moves it toward the back. On Cartesian printers, this is straightforward. There is the axis, motor, direction, nothing complicated. On CoreXY printers, it can be tricky to tell which motor is inverted, where it's looking for end stops, and whether motors A and B are even connected to the correct XY ports. The Voron community came up with a simple diagram to figure this out. From it you can easily see what adjustments to make in each situation. In the end, no matter where the end stops are, after homing, the 0 points for X and Y should be at the front left corner of the bed. Homing speeds is self-explanatory, just don't overdo it. Next is one of the most important printer components, the extruder. At the start of its config block, you'll find parameters for the extruder's stepper motor, set up the same way at the other axis. Then come the hot end specific settings. Nozzle diameter and filament diameter shouldn't need explaining. Heater pin, as I mentioned, my board supports 2 extruders, so it has 2 hot end heater ports. HE0 and HE1. Each had a ground pin and a microcontroller pin connected through a MOSFET for PWM heating control. If you have only one hot end, it doesn't matter which port you use, just make sure to set the correct pins in the config. Hot end heater wires are symmetrical, so polarity doesn't matter. Sensor type and sensor pin are for the thermistor that measures hot end temperature. Like for the heaters, there are two ports, TH0 and TH1. Thermistors usually have no polarity, but there are also digital high temp sensors, but that's another topic. Sensor type is very important. Simply put, a thermistor's resistance changes with the temperature. The firmware uses a resistance to temperature lookup table for each thermistor type. Even though most printers use 100 kΩ thermistors, the resistance change can vary a lot between models. You usually can't tell the type just by looking at it. You'll need to check the seller or manufacturer or look it up on forums. If you set the wrong thermistor type, temperature readings will be incorrect. You can still print by adjusting your temperatures to match your readings, but it's not convenient. Klipper lets you create a custom thermistor type by manually measuring resistance at known temperatures, building your own table and adding it to the config. I use a Bamboo Lab hotend. They don't share thermistor specs themselves, but the community figured out long ago that their table matched the ATC Cimetec 104 GT2. Control defines how temperature is maintained. There are two modes. The first one is watermark. In Marlin it's called bang bang, which simply turns the heater on and off when it reaches the target temperature. I don't recommend using this mode at all, except maybe for filament dryer or a heated chamber. The second mode is PID. Without going deep into theory, it uses a PWM signal calculated from three parameters: proportional, integral, and derivative. You can get this value through a simple calibration command. I recommend calibrating PID at the temperature slightly higher than your normal printing temp. Sometimes it's worth running the calibration with the part cooling fan on, since airflow can slightly cool the hot end and affect heating. Min and max temperatures are more about safety than printer capability. If the thermistor reads outside this range, something wrong. For example, if the thermistor wire breaks, the reading will drop below zero. If it shorts, the reading will jump very high. In both cases, the printer will shut off all heaters and throw a min temp or max temp error. Klipper has other safety settings, but it's best not to change them. The heat bed settings are the same as for the extruder. On the board there are the HB and CB ports. By default, heat bed use watermark control, and that's usually fine, but I prefer to enable PID for the bed as well, and calibrate it just like the extruder. Finally, let's set up the fans. Most 3D printer fans have two wires, plus and minus, and their speed can be controlled with the PWM signal. On most boards, fan ports use the main power supply voltage. Some modern boards let you choose 24, 12 or 5 volts for fans, which is handy if you want to use PC fans, for example. If the fan pinout shows ground and VBB, VFan or V+, it is a non-PWM fan port. It will just run whenever the printer is on. PWM fan ports have a positive voltage pin, and the second one goes to a microcontroller pin for the speed control. There are several fan types in the config. Just fan is the part cooling fan. The only required setting is the control pin, the one you connected the fan's negative wire to. The other parameters either have defaults or optional. You also can set tachometer options if the fan has feedback, but I've never used one. Heater fan, fans that turn on when one of the heaters reach a set temperature. There are many parameters, but you only need to set the pin, the heater, and the activation temperature. For example, start heat break fan when hot end reaches 50 degrees. Controller fan can turn on when stepper drivers or heaters are activated. It doesn't depend on temperature, it starts as soon as the element is active. And temperature fan allows you to turn on a fan based on reading from other temperature sensors, such as MCU or host. These sensors also need to be configured. The last thing worth setting up is the screen. Klipper doesn't really need a screen since the web interface is more than enough to control, but sometimes it's convenient to do something directly from the printer. Simple displays that connect to the exp ports on the board are set up like this. If the board has these ports, in the configuration they will have aliases, which are basically extra names for these pins based on their position in the port. If the screen has two cables, connect them according to the labels. If the screen works with one cable, like old Creality screens, connect it to the EXP3 port on the display and EXP1 on the board. Then go to the configuration examples, find the sample LCD file, locate your screen in the list. There aren't many, but the most popular ones are there. Copy the block for your display and paste it into your configuration. After restarting, the screen should work. Most often with Klipper, people use touch screens. I've only used the Bigtreetech TFT35 SPI. Here is how I set it up. First, you need to have the Klipper screen package installed. In many system images, it's already there. You can install it manually through KeyAuth. Then, on the boot disk on the SD card, where we set up Wi-Fi, there is the file called Ambient-env. In the overlays parameter, set the value to TFT35 SPI. There are also parameters for Klipper screen in the system.cfg file, but in my case, changing only Ambient-env was enough. After rebooting, you should see the screen turned on immediately, and after the system finishes loading, Klipper screen will start. I won't recommend this screen to you. It works, but it's very slow. There are better quality screens that connects via HDMI, though I haven't had those. Old touch screens made for Marlin firmware either don't work with Klipper at all or require very complicated setup. Usually, it's easier to get a simple text display. All the main functions are still done through the web interface. Okay, Klipper has many more features: filament runout, sensors, RGB control, remote access, Telegram bots, and much more. It's impossible to fit everything into one video. So it looks like there will be more videos about Klipper in the future, including printer calibration, macros, and other stuff, if you're interested, of course. As always, thank you to everyone who watched until the end. This video turned out very long and challenging to make. I'll be very grateful if some of you can support the channel financially. It really helps the channel growth and makes new projects possible. For example, I recently bought two old printers, a Creality CR10S and Creality CR10V2, and I'm gonna try to turn them into a big Duender. Or what other name could we give it? Links to Patreon and regular donations can be found in the video description. So, that's all for today. See you soon!